Let's look at another motion problem that involves the antiderivative. In this problem, a car is traveling at 55 miles per hour. The brakes are applied, causing a constant deceleration of 11 feet per second squared. And we are to determine the following. When does the car stop, and how far does it travel? Now, the first thing you notice here, I've got written in red, is consistent units. It's really easy to overlook consistency of units when you're trying to get right to the calculus part. But notice we have a constant deceleration of 11 feet per second squared, but our velocity is written in miles per hour. So the first thing we want to do is compute the feet per second dimension of our miles per hour. So 55 miles per hour, and of course we want to absorb the mile, so we will use the consistent unit 5,280 feet. And then of course we want to absorb the hour, so we use the consistent unit of 3,600 seconds. Now first off, this is not very difficult, but we don't want our equations to have a bunch of decimals in them. So we're going to reduce this. Notice the zeros absorb right off. And so we get 55 times 528 divided by 360. And then of course it would be convenient to get rid of the 5 out of here. That'll just give us an 11. And if you divide by 5 here, you get a 72. We can keep going. Notice here that 8 divides 72, and it also divides 528. And that'll give us 11 times 66 divided by 9. And of course, one more step. We can knock out a 3 here to give us a 3, and a 3 here to give us a 22. So we'll get 242 divided by 3 feet per second. General math, of course, but very important general math. Now, the motion we have from the hypotheses is that A is negative 11. We will take the initial velocity to be what we just computed, 242 divided by 3. And we're going to talk about the fact that we will start measuring time when the brakes are applied. So then that'll just give us a position at time t equals 0 equal to 0, just to make the problem simple to do. Now, of course, acceleration is just the instantaneous rate of change of velocity, so dv dt equals negative 11. And now this is such a simple problem, I didn't even write the integral signs. All we do is, anti-differentiate, so negative 11 becomes a negative 11t plus a constant, c1 in this case. So when it's that simple, you can move directly to v of t. There's no need to write additional notation. And of course now, we're given the fact that the initial velocity is 242 divided by 3, when t is equal to 0, so that zeroes out this term, so the c1 must be 242 divided by 3. So we can go ahead and fill that in. Our velocity equation is equal to negative 11t plus 242 divided by 3. Now that will allow us to figure out when the car stops. Basically, we just need to know when the velocity is 0, and that's a very simple equation. So what I did is I went ahead and used the fact that we know this has an 11 in it, so I factored the 11, so that'll give us a t here, and when you factor the 11 here, that leaves you with a 22 over 3, and of course I took out the negative so it's easier to see. And of course, velocity will be 0 if and only if t is equal to 22 over 3 seconds. So that would be the time that has transpired when the car actually comes to a stop. Now, to get the distance, we just need the position function, and that's easy to do too, because now we know that the instantaneous rate of change of the position is equal to the velocity. So we set this equal to what we just computed for velocity, and then we take the antiderivative. Again, I didn't use the integral sign because it's just add 1 divided by the new power. So the negative 11t becomes negative 11t squared over 2, and the 242 divided by 3 just becomes 242 divided by 3 times t, and plus the arbitrary constant, which we just call c sub 2. And again, we go to our initial condition, x of 0 is 0, so that zeroes out everything. So C2 must just be 0. We're really cooking with gas here. We got very simple analysis to get our position function. So here's an equation for the position function. Now, what we want to do is substitute this time here into x of t to find how far the car actually travels once the brakes are applied. So what I did, I want to go ahead and make the substitution here in evaluation a little bit simpler. So what I went ahead and did is I get a common denominator of 6 here. So I pull out the 6 or factor the 6, and then of course we extract the negative 11t, which we have here. Now when you look at that, 2 into the 6 will give us a 3, so we need a 3, and the only other thing we left behind was the t, so we have a 3t here. Now of course when we take out the 11, negative 11t, we have the 22 left around, but 3 into 6 will give us a 2, so we have to hit the 22 with a 2, and that gives us a 44. So this is not required. This just makes the evaluation a little bit easier. Again, it's your choice as to how you want to write this. And so now we can say x of 22 over 3. So we go ahead and substitute 22 over 3, and that'll give us a negative 11 times 22, and then of course downstairs we'll have 6 times the 3 here. And then of course when we substitute 22 over 3 here, the 3's absorbed, we're left with a 22, and then of course we have the minus 44. So what we can do is just, this is a negative and this is a negative, so just absorb the negatives and go ahead and flip this around. So that'll give us a 22 here, and then of course here one of the 2's and the 6 will absorb into the 22, and that'll give us 11 times 11 divided by 9. And now of course if we wanted to continue with the exact answer, we can write 22 as 20 plus 2, and 11 squared is 121. So 20 times 121 will give us 2,420, and 2 times 121 is just 242. You add these two numbers, they're simple to add. You get 2,662 divided by 9 feet. So that's how far the car travels once the brakes are applied. And then of course if you divide this out, you can get a decimal, 295.8 feet. So now again you can see that the calculus and the motion problems are very much interrelated, and the analysis is very straightforward. The only thing that would make the problem more difficult is that we have a more complicated hypothesis. And we are done.